Hello everyone. Today let us discuss about Kirchhoff's rules. This is a very important topic because we need to solve so many numerical problems based on these rules. Okay, let's start our rules. There are two rules mainly. Why they have made these two rules? Because to solve an electrical network, suppose electrical network means there are so many resistors, capacitors, inductors, or it can be any other component which are connected together. Then we need to solve how much current flows through each branch and what is the voltage drop across one particular device. To solve all these problems, they have made these rules. So these rules are very useful for us to solve the numericals. In our present classes, we have to solve the numericals. But for electrical engineers, they are very useful to solve their problems to know how much current flows through each and every branch, potential drop across a particular device, etc. Now let's start. There are two rules. Let's start with the first rule. So what is the first rule? First rule is called as junction rule, or it is also called as current law, Kirchhoff's current law. So two rules are there. The first one is called as junction rule or current law. And after that second one we will discuss later. The second one is called as loop rule or voltage law. That is Kirchhoff's voltage law. So first let us start our discussion with the first one, Kirchhoff's first law. What is this first law says? So if you take any network or electrical circuit, the algebraic sum of the currents at any junction is 0. Algebraic sum of the currents meeting at any junction is 0. What does it mean? Let us see. What is a junction? Now, if I draw two lines like this, the place where they meet and they touch each other, it is called as a junction. In some networks, they draw like this they draw. Here, there is no connection between the wires. But here, there is a connection between the wires. If you put a dot like thing, the dot says there is a connection between the wires. And if you don't put a dot, and if you draw like this, which I have drawn in second figure, if you draw like this, the second figure, there is no connection. First figure, there is a wire between the two wires. Second figure, there is no connection between the wires. Now, what does it mean now? If there is a junction like this, at the junction, some currents may be flowing inside, some currents may be flowing outside. Then at the junction, algebraic sum of the currents meeting at this junction is equal to 0. Or we can also say, in some other words, the sum of the currents entering a junction is equal to the sum of the currents leaving that junction. Suppose if you have a river comes like this, and another river comes like this. So I'm just taking, they both met together, and they have, like both the rivers, they met together and it has become a single river. This is the first river, this is the second river. Then they met together and flows out, the water flows out like a third river. Then the water in the third river is equal to sum of the first two rivers. The same example we can apply for the current. So the sum of the currents entering a junction is equal to the sum of the currents leaving that junction. Sum of the currents entering a junction is equal to sum of the currents leaving that junction. So mathematically we can write that in the form that is sigma I is equal to 0. Sigma I is equal to 0. what are the sign conventions, or what is a sign convention when you are applying a junction rule? The first one is currents flowing towards the junction are taken as positive. Number 2, currents flowing away from the junction are taken as negative. For example, I will take here two wires flowing like this. Here we have a junction A, and let us say it has gone out into three branches. Let this be I1, let this be I2, and let this be I3, let this be I4, let this be I5. Now in this figure, I1 and I2, they are flowing towards the junction A. So they can be taken as positive. And I3, I4 and I5, they are flowing away from the junction. So they can be taken, that is I3, I4 and I5 can be taken as negative. So this is the sign convention we will be using throughout this discussion, and also for the further discussion in our next topics also. That is, we will also discuss about Wheatstone bridge, meter bridge, potentiometer. In those discussions also we will use the same notation. Now let's go further. So here I have taken a small part of a circuit. Here 5 currents are meeting at the junction A. So in this I1, I2, I3. So in this I1, I2, I3, they are flowing towards the junction. So we will take them as positive. And I4 and I5, they are flowing away from the junction. They are flowing away from the junction. That means I1, I2, I3 are coming inside. I4 and I5 are going outside the junction. Therefore, let's follow the sign convention. I1, I2, I3 we will take as a positive. That is I1 plus I2 plus I3. Algebraic sum means you have to take a positive and negative and add all of them. Then the sum is equal to 0. That is sigma I is equal to 0. Therefore, I1, I2, I3 which are flowing inside the junction, they are taken as positive. Now, I4 and I5, they are flowing away from the junction. Therefore, they are taken as negative. So, minus I4 minus I5 is equal to 0. Or else, take the minus negative signs to the right side. We get Y1 plus I2 plus I3 is equal to I4 plus I5. That means incoming currents are equal to outgoing currents. Incoming current is equal to outgoing current. This law is called as Kirchhoff's current law. Junction rule is also called as Kirchhoff's current law, KCL. KCL. So this is based on law of conservation of charge. This is based on law of conservation of charge. So it is simple. Incoming currents, sum of the incoming currents is equal to sum of the outgoing currents, or algebraic sum of the currents meeting at a junction is equal to 0. Further, let's continue for the second law. Kirchhoff's second law. It is also called as loop rule. Kirchhoff's loop rule. We also call it as KVL. Kirchhoff's second law, or it is also called as loop rule, and because it is related with the voltage, we call it as KVL, Kirchhoff's voltage law. So we call it as like that. And what does it say? It talks about a loop. Loop means like a closed circuit. Like there may be a battery, there may be a resistance or another resistance like this. It is a closed circuit. When there is a closed circuit, we call it as the loop. We call it as the loop, electrical loop. So, just like ordinary loop, here it is an electrical loop. So, if you take a closed loop, a part of a network, algebraic sum of the changes in potential must be 0. Algebraic sum of the changes in potential must be 0. That means there will be potential differences across the devices, as already you know them from the previous topics. The algebraic sum of the potential, if you take together and if you take the sum of all of them, it is equal to 0. Or you can say in other words, algebraic sum of the EMFs in any loop of a circuit is equal to the sum of the products of currents and resistances in it. Once again I repeat, algebraic sum of the EMFs. EMFs means batteries like E1, or suppose if there are two batteries, E1 plus E2, that is sum of the EMFs means E1 plus E2, that is equal to sum of the products of currents and resistances in it. Suppose I1 R1 is one product, plus I2 R2 is another product, plus I3 R3 is another product. Simply I am taking an example and saying like this. Suppose there are two batteries with two EMFs, E1 and E2, and there are three currents in different branches, I1, I2, I3 with resistances R1, R2, R3. Then we can write sum of the batteries, that is sum of the EMFs of the batteries, E1 plus A2 is equal to I1 plus R1 plus I2 plus R2 plus I3 plus I3 into R3. I1 R1 plus I2 R2 plus I3 R3. So what is this? Product of current and resistance. So I1 R1 is the product of current and resistance. I2 R2 is the product of another resistance and current. I3 is the product of another current and another resistance. So if you take all these products and add them, that becomes the sum of the products of the currents and resistances. If you add all of them, that is equal to sum of the EMFs of the batteries. So this is actually easy, but don't get confused. It is simple. If you take the sum of the EMFs of the batteries, add all of them, that sum is equal to products of currents and resistances in it. Products of current and resistances, that is I into R products, if you take and add all of them, that is equal to sum of the EMFs. So mathematically it is written as sigma delta V equal to 0. That is, algebraic sum of the changes in potential must be 0. To represent that sentence, this equation is taken. If you want to take the second statement, that is algebraic sum of the EMFs in any loop of a circuit is equal to the sum of the products of currents and resistances in it. To represent that, the second one is taken, that is algebraic sum of EMFs is equal to algebraic sum of products of currents and resistances. So with this introduction, let's further discuss this law. What is the sign convention? The sign convention, let us see what is the sign convention. When you are analyzing a loop, you can go either clockwise or anti-clockwise. A loop means a closed network, as I said, like this. This is also a loop I am showing you here. So this loop has one EMF, that is E1, R1, R2, R3. We have taken three resistances. So when you are analyzing, you can go either clockwise. This is clockwise. Or you can also go anti-clockwise. That is your choice. So the first rule says we can take any direction as the direction of the traversal. So how you are analyzing, how you are going, that's like how you are traversing. You can take any direction, either clockwise or anti-clockwise. Then the second rule. The second one is the EMF of a cell, it is taken as positive if the direction of the traversal is from its negative to the positive terminal. If it is from negative to the positive terminal, the EMF can be taken as, that EMF of the cell can be taken as positive. Here I have drawn here to show that. So when you are going from negative to positive, which I have circled with the red color, then EMF is taken as plus E. Very clearly I have shown with the figure. And third rule or third convention, sign convention. When you are going, that is when your traversal is from positive to the negative terminal, then the EMF of the cell is taken as negative. This is the one which I am circling with the blue color. So now you can see you are traversing from positive to negative. Then the EMF is taken as negative, that is minus. Then the fourth point, the current resistance product IR, it is taken as positive if the resistor is traversed in the same direction of the assumed current. Whatever may be the current direction, that is your assumption, you have assumed. If the resistance is traversed in the same direction as that of the assumed current, then the current resistance product is taken as positive. And finally, the last point, the current resistance product is taken as negative if the resistor is traversed in the opposite direction of the assumed current. If you are taking a direction, if you are analyzing or if you are traversing the IR product, that is in a direction opposite to the direction of the assumed current, then the IR product is taken as negative. So here I have taken one small network. You can clearly see this. So for that last point, I have taken two small diagrams here, which I am circling with the green color and the yellow color. You can see this. IR product is taken as positive if you are analyzing or traversing the resistor in the direction of the assumed current. In the green circle, the arrow is from left to right. The current direction is from left to right. You are traversing from left to right. Then this IR product is positive. In the second yellow rounded figure, you are traversing a resistor opposite to the direction of the current. Current direction is from left to right, but you are traversing opposite to the direction of the assumed current. Therefore, the IR product is taken as negative in the yellow color one. That is the figures for the last point. Now, let us consider this network and let us completely analyze it. We will take loop by loop. Loop means, already I told you, it is a closed circuit. So here we have many loops. For our discussion, first I have taken the loop ABCFA. ABCFA means ABCFA, this part. So once again I will draw along that so that you will understand. We are traversing like ABCFA. This is the one. Okay. Now let's start our discussion. Algebraic sum of the current resistance products. Let's take algebraic sum of the current resistance products. See first, what is the first product? I1 R1. So we are traversing R1 in the direction of the current. Therefore, we are taking this product as positive, that is I1 R1. Then when you come here, that is I'm showing with this like this blue color. Now clearly you can see there is a R2, that R, but I2 is in the opposite direction of the traversal. Now you are traversing opposite to the direction of the assumed current I2. Therefore, this product will become negative. That means minus I2 R2. Once again I tell you, if you see that, the first one what you are analyzing is I1 R1, that is we are traversing in this direction, current direction is also in this direction, so the first product I1 R1 will become positive. Then after that, when you go like this, in this only one direction you have to follow, either clockwise or anti-clockwise. Here I am following clockwise direction. So when you are going like this, here you have the R2, here you have the I2. I'll remove the blue marks so that you can see clearly. I2 is from our right to left, but we are traversing from left to right, opposite to the direction. Therefore I2 R2 product is negative. So what it will become now? I1 R1 product is positive, but I2 R2 product is negative. Sum of the current resistor products, that is I1 R1 minus I2 R2. In this network, that is ABCFA, how many batteries are there? We have only two batteries. One is E1, another is E2. That is, one is with the EMF E1, another is with the EMF E2. But they are even you are coming from negative to positive. Even you are coming from negative to positive. So I have shown here, when you are coming from negative to positive, this EMF should be taken as positive, that is plus E. When you are coming from positive to negative, then EMF should be taken as negative. So with this notation, now here in this particular example, for E1 you are coming from negative to positive, so E1 is positive. For you E2 you are going from positive to negative, so it becomes minus E2. Therefore, so how we will write them now? Now how we are going to write them? E1 minus E2 is the sum of the EMFs. Then according to our statement, you can see our statement. This one, the algebraic sum of the EMFs in any loop of a circuit is equal to the sum of the products of currents and resistances in it. So we have to equate now sum of the EMFs to the sum of the products of currents and resistances in it. So let's do that now. And now this E1 minus E2 is equal to I1 R1 minus I2 R2. E1 minus E2 is equal to I1 R1 minus I2 R2. This I have shown here. E1 minus E2 is equal to I1 R1 minus I2 R2. With this, the loop ABCFA is over. Let's further discuss about the next one. The next loop we will take is CDEFC. CDEFC. So once again, I'll write CDEFC. So we are going from CDEFC, that upper loop I am taking now. So here in the upper loop we have only one EMF, that is E2, and you are traversing from negative to positive. So negative to positive means it is plus E, as already we have discussed. Therefore here you will get now, that is what you are going to get now is E1 is the, E2 is the only battery here, E2, that is the sum, means there are no other batteries, so only one E2 is the total sum, that is equal to product of the currents and resistance. Now if you see, this is a resistance R3. Into the R3 the current flowing is I1 plus I2. Therefore you have to write I1 plus I2 into R3, because both the currents added together, that is I1 comes like this, I2 comes like this, they are added together and became I1 plus I2 here. That is, sum of I1 plus I2 is flowing through R3. Therefore you have to multiply R3 with I1 plus I2. So let's write now, E2 is equal to I1 plus I2 into R3, and what else is in that loop? Another resistance R2. In R2 current flowing is I2, so we can write plus I2 R2. So this is the final formula. Now you are traversing the resistance R2 in the direction of the current I2. Therefore it is taken as positive. You are traversing the resistor R3, that is R3, in the direction of the currents I1 plus I2. So that is also taken as a positive. So let's write now finally what we are going to get now. Let us see. That is E2 is equal to I1 plus I2 into R3 plus I2 R2. So this is the second law. This is also called as Kirchhoff's voltage law, KVL. This law is based on the law of conservation of energy. With this I have clearly explained both the laws, and we will apply them in the next derivations, that is for Wheatstone bridge, meter bridge, potentiometer. Same rules will be applied, and these are also very much useful when we go to the 7th chapter, that is AC currents. So in that topic also it will be very useful for us. These two are very much useful. So let's let us learn them, and then be careful to how to apply the notations. Sorry, here it is removed, so I am trying to write it again. So these are the two laws which we have learnt now, that is KCL and KVL, and we will apply them in the next coming networks in the next videos. We will meet in the next video with another topic. Till then, bye. God bless you all. Thank you. God bless you all.